Uh, it's my great pleasure to introduce Samarjit Chakraborty. So Samarjit is a William Kennan Distinguished Professor and the Chair of the Computer Science Department at UNC Chapel Hill. So prior to joining UNC Chapel Hill, Samarjit was a full professor in the Department of Electrical Engineering at Technical University of Munich from 2008 till 2019, which I had overlapped with him for 5 years. And so he was the chair of he held the chair of the real-time computer systems. And from 2003 till 2008, he was an assistant professor in the computer science department at the National University of Singapore. So Samarjit received his PhD from ETH Zurich, and he got the ETH medal for his PhD thesis, and he also got the European Design and Automation Association Outstanding Doctoral Dissertation in 2004. So he and his student, they have several research awards, including CSA and MOBISys, and also 2019 ACM transaction on design automation of electronic systems. So he's a fellow of IEEE, and more importantly, a few months ago, he got the Humboldt Professorship Award from the German federal government. So every year, they're only given to 12 scientists across the globe, and Samarjit was actually one of the recipients, and it comes with a €5 million grant, right? So, and maybe I can give a short joke about that, if you don't mind. So, actually, Samarjit and myself, we moved at the same time. So we're deciding to move. And then he was trying to encourage me that it's a good move. He said, look, when we move, we are eligible to apply for Humboldt. If you're inside Germany, you cannot. You have to go outside. So I guess he made it a reality. So he applied and he got it. So thank you, and the floor is yours. So can you all hear me? Okay. So thank you, Majid. It is indeed very nice to be here. This is my first visit to Colorado, and I have in Munich, when I drove back home, I could see the German Alps, and this is unfortunately not something I get to see in Chapel Hill, in North Carolina. So it was very nice to see all the mountains when I was driving from Denver to Boulder. And you know, I know a lot of people here, Sriram, I've met Ashutosh in conferences before, and you know, we do a lot of similar work. So just to respond to what Majid said, you know, I don't remember quite telling Majid that, and even if I have said that, that is not, you know, I didn't quite plan things like that. It was really a coincidence that it would happen. So I do a lot of different kinds of things, and a lot of my recent work is in line with things that Majid and Sriram and Ashutosh and other people do here. So I thought that, you know, rather than, you know, talking about things they already know very well, I would rather talk about things that most likely they do not know. So that's the reason I decided on this talk. And before I start, I sort of intentionally wrote up like a tongue-in-cheek kind of an abstract, and I wanted to ask, does anyone have a good guess on what this talk is going to be about? In fact, you know, this is the second time I'm giving this talk. Last time I gave, last year I gave it at NC State, and I then thought of doing something like, you know, I'll say that I have $5, and you know, the first 5 people who can guess the topic of the talk, I'll give them like a $1 prize. But I'm not going to do that because there is limited time here. So let me, you know, go straight into the talk, and I hope that this works. I think you need to click on the screen, and then it will work. Yes.
I want to.
You first.
Yes, so this is what the talk is about. It is a talk on sustainability. And I don't know how many of you have like one mobile. I'm sure all of you have a mobile phone in your pocket. It's better to put them in silent mode. But how many of you also have a spare phone at home in your drawers, like one phone? How many of you have two spare phones in the drawer? How many of you have three spare phones in the drawer? So you see that, okay, there is at least one hand. So we all have a phone and we have multiple phones sitting in our drawer. I'm still using an iPhone 8. My wife uses an iPhone 13. My 8 is still working fine, but it is already showing signs of aging, right? And the kind of aging that I am seeing is that now I charge the phone in the at night, and in the morning it works, and towards late afternoon, depending on what I have done, it sort of slowly the battery kind of sort of says that I don't have enough juice anymore. So let me give you some statistics. Like there are 57 million phones that are dumped in the US per year. This is already data from a couple of years ago. 70% of these go to landfills. 30% of the waste in landfills is actually electronic waste. And a couple of years ago, or let's say 10 years ago, we changed our phones because new phones were actually better. But today, frankly speaking, I don't see too much of a difference between the iPhone 8 and the iPhone 13. The camera might get a little bit better, but one of the main reasons people keep on buying phones is because the battery ages over time. And for many devices like iPhones, you cannot quite very easily change that battery, right? And so battery life is a major concern when people today buy phones. And in some of the surveys, people said that for a large number of people, just battery life is a major buying decisions. Many of these mobile devices like smartphones today are no longer, unlike let's say 20 years ago, these are no longer low power devices. They have fairly powerful processors. Of course, the display network, all of that uses a lot of power. And also today, we do a lot of work on this mobile phones. Like most of the browsing these days we use a mobile phone. Most likely, you are reading more emails on your mobile phone than you are reading on your laptop. Now, to give you an idea of what is going on in your phone, these days, phones have electrically powerful processors. These are heterogeneous multi-processor devices. So they have different kinds of processors. And in most phones, they use what is called a big little architecture. So it has one big processor and one little processor. And the big processor does, the big work, but also consumes more power. The little processor does, less work, but it's also low power. And each of these has 4 cores. Now, in the case of this big processor, the A15, just to get an idea, if you just switch on one, and each of these processors can run at multiple voltage and frequency levels, right? So each processor supports multiple voltage frequency levels, and your operating system has a governor or a power manager. And at runtime, it is continuously changing the voltage and frequency level, right, in response to the load on the processor. So if there isn't too much load, it is running at a much lower frequency because there isn't so much work to do. Frequency means that the processor is running slower, but it is also consuming much less power. Whereas the moment you start playing a game or watching a video or do something more computationally expensive, the processor's frequency and voltage correspondingly is going to jump up, and it's going to consume a lot more power. And just to get an idea of what that difference is, if there is only one core in this big processor running, and it is running at the lowest voltage and frequency versus if all the 4 cores are running at the highest voltage and frequency, there is a 10x difference in power consumption. Okay? So there is significant difference. Now, in terms of controlling the power consumption, there are multiple knobs that are today available. You could turn off parts of the hardware. You could dynamically change the voltage and frequency. You can decide on which processor to use, the big or the small. You can also decide on which port to use, and all of that is going to have an impact on the power consumption. Right? Now, therefore, coming up with the best possible, power management strategy is actually a difficult problem. Now your operating system already does that, and you think that it is doing a fairly good job, but unfortunately it is not. I mean, there is a lot of potential in terms of what can be done to make things much better. Now, on the other hand, so this is about I charge my phone, how long can I use my phone before I charge it again? The other thing that is happening is that, as I said earlier, the battery is actually aging, right? So when you buy a brand new phone, you charge it, and with that one charge, it probably lasts certainly one day, maybe even 2 days, and 3 years, 4 years down the line, you again charge it to this full capacity, but it you do the same things, but it doesn't last for 2 days. It probably hardly lasts for a day. So why is that happening? Because the battery cells, their charge retention capacity is decreasing over time. And how much that retention capacity decreases, it depends a lot on what you do. So for example, in this case, you see there are two users. So there is a one user who is the red user and charges the phone. So it starts from 100% and then it goes down to this level, not too much, slightly around, let's say 45-50%. And then charges the phone is charged to 80% and then again discharge and so on. Whereas the blue user kind of deep discharges the phone, the battery kind of is almost zero, and then again charges to 100% and then again deep discharges. So which user do you think is more friendly towards the battery, the red or the blue?
The red.
The red is much more friendly because if you do this deep discharge and then a full charge, it's actually aging the battery much faster. So if you are, for example, going on a vacation and you don't want to use your phone, it's actually not a good idea to completely discharge it or completely charge it and then keep it. Right? The best thing would be to sort of charge it at a middle level and then keep it. And there are various reasons related to electrochemistry. I cannot go into the details of that. So the whole idea is, how you use the phone, that is going to, affect the battery a lot, right? Also, for example, I don't know how you charge, but most people, before you go to sleep, you are going to, plug in the battery, the phone to the charger, and in the morning you take it out. This is the usual thing people do. Very bad. So this is actually killing your battery. So it would be much better if you, for example, what is happening is that the battery is getting charged to the full capacity. So let's say you go to bed at like 10 in the night. By 12, the battery is already at 100% charge and you are using it from 7 in the morning. So from 12 till 7 hours. So it's almost like 1/4 of the day, the battery is at the highest charge level, and that is significantly accelerating the aging. So it would be much better if you, let's say, get up at 5 in the morning and then plug the phone in and go back to sleep at 7. Not very convenient. So you could actually buy one of our smart chargers, right? So that smart charger is going to read your calendar and see when you plan to get up from the alarm. And then although you plug the phone in at 11 in the night, it will only start the charging from 7 to 5. So this way you prevent the battery being in this very high charge state for a long time and thereby help increase the aging. And similarly, if the battery or the operating system also knew what exactly you are going to do, right? You probably, are you going to use your GPS and connect the phone to your car, or are you not going to use it? Are you going to come to your office and plug the phone to the charger? If all of those things could have been known, then the operating system and the battery manager could have done a much better job, right? But unfortunately, we do not know that. So it is actually doing everything to help you better use the phone, but everything that is doing is very unfriendly towards the health of the battery. Okay. So the main point, because your department chair has to go, I told you that I'm going to give the take-home message within the first half an hour. So the main idea is that current governors, what they do is these governors actually are reactive governors, or power managers are reactive. What they are going to do is they look at the load on the processor, and then on the basis of the load, they try to increase the frequency. And when the load goes down, it decreases the frequency. And this is actually not a very good idea because you are always increasing the frequency too much, or you are increasing it too much and then again increasing it too much. Instead, what we would like to do is we would like to design governors which are proactive, right? So we look at what has happened in the past. or we try to understand what the user is going to do, and on the basis of that, we take proactive decisions. And as a result, you can do much better management. Similarly, so this is like similarly for applications, right? Currently there is no communication between the application and the power manager. So the power manager doesn't quite know what the application is going to do. Whereas if the application would have had some API through which it can communicate with the power manager, then the power manager would have done a much better job in doing it. Right? So the question is, how do you enable that? Similarly, if, as I said, if the operating system would have known what exactly are you going to do, when you are going to charge the phone, how much charge is needed, it could also do a much better job in terms of prolonging the health of the lifetime of the battery. So the main idea is that what we would like to do, both for better power management as well as for better battery health, is we would like to do what is called, or what we call, deep customization. So what is the meaning of deep customization? Deep customization means that, first of all, we would like to customize the power manager on the basis of the application. We would like to understand what the application is doing and going to do. Secondly, we would like to customize the power manager on to the users, habits. We'd like to learn what the user does, and then do the customization. And even we would like to go one step further. And so things like if you are doing web browsing, we would actually like to come up with a specific power management strategy for each website. So if you are going to CNN, the system knows, oh, CNN has this kind of workload, so the best power manager will be that. Whereas if you are on Facebook, it knows that Facebook has a different workload, so this is the best power manager. So all that I'm going to do for the rest of this talk is I would make a case for this customization. Okay, so the talk is not going to be too technical. I will try to keep it at a level that everybody understands. And I would like to impress upon you that there is a lot of work that can be done in this space, right? And in particular, there is a lot of work in terms of machine learning actually that is possible. And that interacts very well also with computer systems, like operating systems and so on. So the kind of things we need to solve, or we need to do prediction at two different time scales. At a very small time scale, the time scale at which workload is changing, and also do a prediction at a much bigger time scale in terms of how the user is doing, right? So there is prediction at both time scales that are needed. So we also need to model user behavior. And finally, there is also a lot of scope for designing appropriate APIs such that the operating system and the power manager can talk to the applications. And also there is a lot of scope for developing algorithms. And I will also show you what kind of challenges are there in terms of developing algorithms. So that's essentially like the end of the main part of the talk. And for the rest of the time that I have, I will essentially illustrate how these kind of techniques can be used in many different contexts, right? In the context of phones and games and cars and drones, right? That is where the title comes from. So in the case of games and phones, let's start with how to do this in the case of, I'll start with computer games, right, that you play on phones. And we have been doing, so the work that I'm going to talk about is work that we have been doing over many years now, more than 10 years. And a lot of this work was actually funded by Intel and by Google, right? So, and we would not have been able to do this work, not because of the funding that they gave, but we were able to implement a lot of these systems in real applications in the Chrome browser. And so I do not know how much of this work Google can finally implement it. But without their help, we would not have been able to really get into these systems and do this development. So let me start with how this works for games. So in the case of so we are talking about you playing a computer game on a smartphone. Okay. So like video, a game actually is made up of a sequence of frames, right? It is just that the frame is getting generated based on what you are doing, right? You do certain things, you take a gun and run, and that's the frame that's going to be generated. So there is the start of the frame, then there is the processing, then the end of the frame. So we would like to measure what is the workload of this frame. And on the basis of that, we would like to predict what is going to be the workload of the next plane. And if we can do that prediction, then we can set the voltage and the frequency. So if that prediction is bad, then either the quality of gaming will go down, which we do not want, and if the prediction is bad in the other direction, you are just spending too much energy, right? So the main idea is that how do I accurately predict the workload of the future by looking at workload in the past and really give you the best possible application experience and also give you the at the minimum possible energy consumption. And it's essentially the same thing that will be true in many cases. Like for example, if we are trying to be friendly to the aging of the battery and don't charge it enough, and then you use it, and when you need to make a call, you cannot do that, or you are driving your car and suddenly the phone goes blank, that's also bad. But at the same time, how can we support you in the best possible way and meet your needs, but at the same time do that with the minimum energy and the best possible battery health? So as I said, if you do not do any dynamic voltage frequency scaling, you always run everything at the highest frequency, then the quality is very good, but there is too much energy wastage. And similarly, if you do something such that there is a deadline miss, then the quality of the gaming actually reduces, right? So to give you an idea of what goes on, I do not know how many of you are familiar with Jetpack Joyride. This is a very old game, okay? And so here, if you do not use any power management whatsoever, then this is the total power consumption, and this is the gaming quality, right? So this means that there are still some deadline misses. So your processor is not able to handle the full workload, right? But there are very few misses, you wouldn't even realize anything. If you use the Android default governor, then you save a lot of energy, but there are more deadline misses. You might not even realize this, right? 20% deadline misses. On the other hand, if you have an oracle, right? This is a theoretical construct. If you can exactly predict what is going to happen in the future, then you can bring this power consumption to half of what currently Android is doing, and really also get the theoretical best possible quality, right? Minimum possible. Yes. There is no, as I said, right? These are really, you are missing, this, there is a certain frame rate that the game is trying to achieve, let's say 40 frames per second. It's just that there is a little change in that frame rate, and you might not even perceive anything. So it totally depends on what the game developer has decided. Okay. So the question is that, can we reach this optimal limit, right? Can you design a power manager that, reaches this optimal limit? So essentially what happens is that the power manager should, or what we would like to do is we would like to develop a game-specific power manager. So it predicts the workload as best as possible and then does the frequency voltage scaling, because you'd like to know that in advance. Once things have already been done, then there is no point in knowing. So then you can really measure and see what error you made. And then you use the prediction and the error in order to improve your prediction in the future, right? That's the basic idea. So the first thing that we did, and this is many years ago, people have, if you can see this reference here, this is like a paper from 20 years ago. This is one of the earlier papers, starting to do power management, and they did it for video applications. And all that they did was they used a controller to try to do this prediction as accurately as possible, right? They are using a PID controller, so all that you need to do is you need to get the best possible gain values of the proportional integral and the derivative parts. Now here, what turns out is that, these are, Explore one is one game, Shooting one, Massive one, these are, different games and different gameplays. So what you do is you take one game and you tune the parameters of the game values based on that game, and you take those parameters and apply it to a different game. So here you tune it for Explore one, but then you apply it to the other games, and you see that they are probably not going to do that well, or you tune it for all of them and apply. So similarly here, this is like Massive one. So it works well, sorry, for this one. But on this game, if you use the parameters that have been tuned on other gameplays, then you do not get that good a performance. But the bigger issue is really that if you do it like this, it turns out that in the space of these game values, for most game values that you choose, the system is even going to be unstable. Okay, so in this particular figure here, these planes that you have here, So only values that lie on these planes, they lead to a stable controller, and only these red points that you see here, they lead to controllers that have less than 10% deadline misses. So most likely, if you just randomly pick up some points or some gain values, you are going to get a controller that is even going to be unstable. And this is essentially the, so to speak, like a Pareto front, where this is the power consumption and this is the deadline misses. If you can tolerate a lot of deadline misses, then of course you have very low power consumption. But if you want to reduce the number of deadline misses, you will end up spending more power. But the main idea is that choosing the right kind of gain values becomes a big problem, right? And especially you cannot do that for possible gameplay. You want to do that for one or more plays, and then that should work on many other.
So instability literally here means that your voltage and frequency are just going to go all over the place. And what you are desiring is like a steady voltage.
Steady voltage, and also that might actually result in also very bad power consumption. That we do not want that kind of swings. Exactly. So then what we try to do is that, well, that didn't work for games, although it worked for other kinds of applications before. So we said that, okay, let's try something else. This is not really a control problem. This is actually a prediction problem. So let's look at a predictor, right? And let's look at a linear predictor. So we say that, okay, the workload of a frame is going to be a linear combination of the workloads of the past frames. And the main thing is that, how do you determine the weights of this linear combination? And we said, okay, we could learn these weights. So the main only parameter that we need to decide is the learning rate. And, we kind of empirically, with lots of gameplays, we empirically determine the learning parameter. And to our great surprise, it actually works very well, right? So you start with one game. And here, for example, you see that, the values of the weights start stabilizing. And then, in between, you take those weights and switch over to a different game, it actually stabilizes in value. So this is great, right? It works wonderfully. So we said that, enough, we have solved the problem, published a paper, and we are done. But then things started changing, right? And these results that I showed you, these are from several years ago, where smartphones were very different, and in particular, they did not have GPUs, right? And so all the graphics rendering was actually happening in software. But then the games changed, right? From Quake 2 in 1997, we had Crisis in 2011. Although this 2011 might look very old, there is a new Crisis that has been released in 2020. I don't know how many of you have played Crisis. Okay. So there is a new Crisis that came up in 2020. In fact, this is a game from a German gaming company, and it also I think I don't remember which year it won the Deutsche Computer Spiel Prize, which means the German computer gaming prize. So this is not a sort of an application that a gaming application that you can just ignore. So first of all, these applications changed a lot, so now they have GPUs, they have a lot more graphics, there is physics, there is AI, and most importantly, unlike those old games like Quake 2 that we experimented on, these are closed source games, okay? And that changed everything. So the closed source means I cannot measure when the frame is starting and when the frame is ending, and therefore I also cannot measure what was the workload of the frame. That I could do very easily. If the source code was available, I could just engineer the source code and measure the starting time and the ending time, right? So, that sort of was a big, block for us. So the question is, okay, there's no point in doing this research if you cannot really apply that to real games, which are closed source games. So what we then did was something very interesting. So we said that, okay, the way these games are going to work is, although the entire the source code is close to you, but it is making calls to graphics libraries. Okay, it is making calls to standard like OpenGL or DirectX graphics libraries. So what we could do is we could jailbreak Android, and we could intercept those calls. So if you can intercept those calls, then by analyzing those calls, you might be able to figure out what the game is doing, right? When the frame is starting, when the frame is ending, when is there a level change, when something new is being loaded, and so on. So we could, using that, try to estimate what is going on, and then we are again back in business. We can just apply the same kind of techniques. We could again use that linear predictor and now do power management for closed source games. So, this was kind of the architecture, and there is the GPU, and also for GPU, we could do the same thing, but to our great surprise, now the weights did not converge anymore, right? So now the weights all started completely diverging, and the result of that is this is a completely different kind of work, right? Compared to where everything was happening on the processor, now you have the GPU, now you have this, and it's a completely different beast altogether. So then we said, okay, what else can we do, right? So then we said, okay, now we need to move beyond just a linear predictor. So there is all this work in time series analysis. So why not use the ARMA, like a auto-regressive moving average kind of a model? There, all that you do, essentially the basic idea is that, again, you do a prediction of a workload on the basis of what has happened in the past. But then you also have another polynomial, which is essentially trying to model the error that is happening. And you also try to account for that error. And that error is also evolving as a function of past efforts. So there we could actually train the different kinds of, so these are essentially the auto-regressive and the moving average parts. And we could again train these weights offline. And there are standard techniques for doing that. And it turns out that this actually works very well. Right, so you could actually do this training for a few games, and it works very well with lots of other games. And this is a comparison that shows that if you compare that with the Oracle, so here you have what is the percentage of this processor frequency usage, what is the percentage of the other processor frequency usage, and it actually turns out for multiple games like Need for Speed and Crisis, we are doing very close to what the Oracle is going to do. So the question then, is, how did we proceed? We started with this PID. It, didn't work very well. Then we said, okay, we could use a linear predictor. It worked for some games. Didn't work for the more modern games. And then we said we can use techniques from time series analysis that work. And should we just stop? Is this the end of the line, or can we do something more, right? And the most obvious question is, can we now use some machine learning techniques? Would they buy us anything, or is this a closed problem, right? So that's the natural question. Yes.
Do you have an intuition why ARMA works better than PID? Because this is also intrinsically linear, right? The equation you showed was linear. So
I must admit that these workloads and the interactions are such that we, frankly speaking, we don't have a very clear idea, right? And I think there are just so many components, and also the operating system is doing lots of different things. Like reproducing these experiments itself is kind of so we in fact did some interesting work, and we tried to answer this question, right? Is there a need for something more? Is there still room for improvement? So I could give like one full talk on that. How do you measure things in the ideal case? Right. And we actually got a best paper award for that. Before you do start off doing some research on something, can you just measure what is the potential for improvement, right? That is going to justify that, yes, it makes sense to spend effort. And this is the answer, again, coming back to our old game, Jetpack Joyride. So this is where what happened with all of these games, these new things that we developed, and this is the Oracle. So you see that there is still a gap, okay? There is still a significant gap here. And if you look at more complex games like Crisis, the gap is actually even bigger. And there is also a gap, of course, here. So this essentially says that, there is more that you can do, right? It is just that ARMA is working better, but, it is not the best possible thing you could possibly do. So the first question is that what else can we do? Is it really the best thing to just look at the past workload and try to do a prediction on the basis of that? Now, if you think of it, what is happening is there is some software running on your processor, right? Now, there is an immense amount of data that you can gather, right? So when your program is executing, you have all sorts of events that are happening on the GPU. There are things getting written to different registers. There are different cache misses that are happening. There are different memory accesses that are happening. There are different kinds of instructions that are getting executed. Now, this immense amount of data that you have, the obvious question is if I can analyze all of that data rather than just lumping everything together as a workload, can we do a better prediction of the future? Now, the obvious systems question there is, how do we even monitor all of these things that are happening? Now, for those of you who have done some, computer architecture, you might know that modern processors have like some special purpose registers. These are called the performance counters, right? So you could actually record many of these events, but it turns out that the number of performance counters you have is relatively few. Okay, so there are literally a couple of hundreds of events that are out there very easily, but the number of performance counters are less than 10. So the interesting problem is that, of course, you do not know what is interesting. Ideally, you'd like to measure or keep track of all of them and create a model. Now, the interesting thing is that at any point in time, out of the, let's say, 100 or 200 or 500 things that are there, you have to decide on which 10 you'd like to monitor. Okay, and you keep track of those 10. And on the basis of that, you create a model. And then you move on to a different set of 10. Not necessarily completely disjoint, but something else, right? Because these parameters you have already monitored for some time. So you move on to that and you decide on that model. And then after that, you move on to something else and you decide on those and keep on updating. And this way, hopefully create a better model. So the basic idea is that, you have some system. You cannot have a full view of the system. At any point in time, you can only have a partial view of the system. Like you have only 5 eyes, right, using which. So you have to decide which parts of the system you are going to see. Now, of course, this is a dynamical system, it is evolving. So what is the optimal strategy of observing such that you can create a good model using which you can predict what is going to happen in the future? And that I feel is a very interesting problem. And as systems are becoming more complex, you could actually try to look at this. This will not only have applications in this particular problem we are interested in, but it will also have applications in many of larger computer systems. Now, having talked about that, let me quickly move on from games to like browsers, right? And these days, of course, we are doing a lot of browsing on the phone. And here, the figure that you see is that, so if you, again, what you like to do is rather than using the default governor, we would like to use design a power manager or a new governor that is browser specific. This is the what we did with Google. Now here, the on-demand governor is the Android default on-demand governor, and the browser governor is what we developed. And you can see that the browser governor is going to take 40%, consume 40% less energy. This is when we are browsing Reddit. And you can already see from the plots here, this is the blue line is the A15 and the red line is the A7, the little processor. In this case, the big processor is running at the highest frequency level for a lot longer, whereas here you see it is, it is using that highest frequency level a lot less, and you are benefiting a lot. So the question is, how do you do that? Now, it turns out that, here, as I said, we have the A15 that you see here. This is the A7, okay? And so these are the A7 and the A15 cores, and there are lots of different things you can do, right? So first of all, you can say that, the frequency level for the big processor is from 1.2 to 2 gigahertz, but you could decide that I'm going to limit that. I'm going to use the same Android governor, but I'm not going to allow it to go to 2, right? And I'm going to cap that at, let's say, 1.6, or I'm going to cap that at even 1.4, right? It can do its power manager, but it's just that power management, but it's just that I'm not going to let it go beyond that level. So this could be one thing of limiting the frequency. You can change the governor, of course. You could also do things like limit the utilization of certain cores. So the interesting thing is that you can do voltage frequency scaling separately for the A15 and the A7, but you cannot do that for individual cores. So once you use the A15, all the 4 cores will run at the same frequency. Okay, if you use the A7, all the cores are going to run at the same frequency. But what you can do is you can say that I'm not going to map any thread to 3 of the 4 cores. Okay, and I'm going to use only one of them. Now, intuitively, this actually doesn't sound like a very good thing to do, right? Because you are running it, why don't you use it? It turns out that it's actually a great idea, because although the processor is running, if you don't run anything on it, there is a lot less switching that happens, and the total power consumption is going to be much lower, right? So therefore, you have another degree of freedom as to out of the 4, are you going to use 1 of them, 2 of them, or 4 of them, and so on. So again, there are lots of different techniques that you can do. If you use the standard governor, as I said, it kind of is a reactive governor. So it just looks at the utilization and changes things, and it does not do a very good job. Now it turns out, so these are a lot of what I'm talking about are really empirical results. So it turns out that if you look at the workload of the browser, there are many different threads that are running, right? And the workload involved in each of these threads, this depends a lot on what is the website. So for example, here you see this color is the browser thread, this is the renderer thread, this is the GPU process. So if you look at, let's say the relative workload, then in the case of eBay, the distribution is like this, right? There is the compositor time versus the renderer is like almost 50-50. Whereas if you look at, something like, CNN, then that distribution is very different. So the main point I'm trying to say is that although it's the same browser that you are using, the amount of workload that is getting generated depends heavily on which website you are visiting. And that means that if you could have a power management strategy that you have developed offline for individual websites, you could actually trigger that. So the market I'm kind of trying to allude to is that the governor or the power manager is now very intelligent. It learns that, okay, you typically visit these 15 pages, right? You read the New York Times or you do Facebook, you go to CNN, and it downloads those website specific governors. So not only is it tuned for the browser, but it is also tuned for that website. And when you are visiting that website, it is actually using that governor, right? Because you know that each website triggers a very different workload. Now it turns out that, if you, for example, do something like the A15 frequency capping, if you limit the frequency, then here, on the top, you see how the energy consumption changes for different frequency caps. If you cap it at a very low frequency, the energy consumption is less. And here you see what is the loading time, right? The loading time is kind of the performance that you see. So if you cap the frequency, you can save a lot more energy with very little change in the loading time, right? And this would also depend a lot on what kind of website you are visiting. Similarly, if you restrict the usage, as I said, these are different usages where in the first case you allow threads to be mapped to any of the 4 cores versus you don't use the A15 at all, or you use only one. Then again, depending on the website that you are, this is like the case 1, case 2, case 3. In the case of eBay, between case 1 and case 3, there is a 15% change, whereas in Wikipedia, there is a lot less change, right? And again, all that I'm trying to say is that I'm trying to make a case for you or the system trying to come up with a predetermined policy for each website and storing that and then using that at runtime. Now, the other thing that happens is that when you are doing this browsing, your browser is essentially, your application is moving through multiple stages, right? If you look at how do you typically browse a page, what you do is you read something, then you scroll, and then you again read, right? Now, the browser also tries to maintain a certain frame rate. It is refreshing things at a certain frame rate. Now you will be surprised what Google does is it always keeps the same frame rate. There is something called RAIL, right, which is like a specification of what kind of quality we should maintain. And that specifies that it's always going to be the same frame rate. Now, if you think of it a little bit, when you are not doing any scrolling, but just reading, you do not need a high frame rate. Similarly, when you are scrolling, you cannot, if you scroll fast, you are not scrolling and reading. Again, you do not need a high frame rate. The only time you actually need a high frame rate is when you are scrolling slowly. So therefore, rather than always doing this high frame rate refresh, which is consuming a lot of energy, if you can figure out what the user is doing, and on the basis of that, adapt the frame rate, you will save a lot of power. Now, how do you do that? This is actually very easy. You can record all these tap events, right? So based on the sensing this scrolling or the tapping, you can decide on which mode you'd like to go to, and then trigger a mode specific power manager rather than having a uniform frame rate and a uniform power manager for everything. So again, if you do this kind of different power management strategies, looking at what the user is doing, you will essentially be able to save a lot of power, and that's the main message. Okay. And essentially the same thing here in the load phase, depending on which website you are visiting and what kind of phases are there, and if you use these different phase specific strategies, then overall you will essentially do a lot of power saving. So the main message I would like to put forward to you is that what we need is, on one hand, we need some sort of a communication between the application and the power manager. And if there would be these interfaces and the application can properly communicate to the power manager what it is doing, then overall the power manager has a lot more room. So I will quickly cover the other two parts, and I had the drones in my title, and some of the work that we have done with drones is very similar. Here the issue is, and let me give this example. I was talking about this earlier today, that Amazon has this what is called Amazon Prime layer, right? It has not quite launched out very well, but the basic idea is that you can order something, a package of less than 5 pounds, and Amazon is going to deliver that to you within 30 minutes in your backyard or in your balcony. Now, these are going to be done using drones, and the drones are going to run using batteries. But unlike in electric vehicles, in the case of a drone, the battery is discharged at a very, very high rate. Okay, so this means that aging of these batteries are very fast. So if Amazon actually sets up this business, one of their main costs is going to be that their batteries are going to age out, and they will have to continuously replenish their stock of battery. Now, number one, this is going to be a big expenditure. And the second thing is also that it will also have a big environmental impact. Now, as of now, we are not aware of any techniques on, for example, let's say in the city of Munich, right? If Amazon decides on a warehouse in the center of Munich, and most of the orders come from Munich, then the drones are going to fly much smaller distances, but they are going to pay much more in terms of rental of the warehouse. Whereas if they have the warehouse outside Munich, then the drones are going to fly bigger distances. So the rental is going to be less, but there will be a lot more expenditure in terms of replenishing the stock of batteries. And there, we are not aware of any studies that actually models this and comes up with a appropriate strategy. And the second thing is that, again, I'll maybe because of time, I'll not go through all the details. The main idea here is, so the batteries, depending on how the batteries are dealt with, there is going to be battery depreciation, cost depreciation due to aging. And so there is electricity cost, there is battery cost. And if the management is done properly, and I'll talk about what kind of management, then there is a potential for doing a lot of cost savings. Now, the basic idea is that there is a detachable battery in the drone, and this kind of detachable batteries people have also talked about in cars, but in the case of drones, this is a lot more feasible. So a drone completes its mission and comes back, and you take the battery out and you are going to put a new battery, and then you will send the drone off for the next mission. And the main idea is that how do you do that, right? Now, first of all, there could be lots of different kinds of packages. There could be a 1 pound package versus a 5 pound package. There are also different kinds of batteries. There is a smaller battery versus a bigger battery, or the other option is you have the same kind of battery. So if you use a very big battery for a very small package, then you are unnecessarily increasing the weight of the drone. And also, therefore, it is prolonging the discharge and having higher aging of the battery, which you do not want. The second thing is there will be, let me sort of skip this slide and come here. The second thing is that also, so this is essentially the mapping between the battery and the package. The other issue would also be that, you have a 100% charged battery, there is a flight, the charge goes down, then you charge it again, and then you use it. Is this the right way of doing it? Or do you only need to charge the battery till maybe 60%? Because the package that you are going to send now, and the distance that the drone has to travel, with just a 60% charge, this is enough. Now, this is actually going to play a big role, because if you charge it to 100%, as I said earlier, that is going to accelerate the aging a lot. Okay. The other thing is also that when the drone comes back, you take the battery, do you charge the battery immediately? Because the next mission might be 2 hours later. Or do you actually start charging the battery 15 minutes before the actual mission? That will also have an impact on the aging. So the main problem, therefore, is you have all of these different orders that are coming in. You have a bunch of drones. We are talking about large numbers. You also have a bunch of different batteries. So how do you manage this entire system, right? What is your charging strategy? What is your battery selection strategy? Do you do fast charging or do you do slow charging? If you do fast charging, the electricity requirement is different, but the aging is also different. The waiting time before the order is satisfied, that is different. So the question is that, what's again, these are all of the different control knobs, and the question is, what is the best strategy to minimize battery aging, to minimize cost, to minimize waiting times. And, we have looked at many different strategies. And if you, for example, do random versus you just do a greedy versus you do a optimized strategy, there could be huge differences in battery costs, right? Again, I'll sort of leave at that without going into the details. The last thing I would like to talk about, and before I stop, is that we are all, today more inclined towards buying electric cars, right? We had this conversation with Majid, and Majid is very interested in electric SUV. But one of the main issues is that battery technology has not quite matured. Okay, so you should be very careful before you choose an electric car. Now, Tesla is still fairly new. We haven't quite reached the stage where a lot of Tesla owners are going to have batteries that need to be replaced. And once that starts, then this is going to be a completely different scenario. And a battery is actually the most expensive component in the car, right? So if you need to replace the battery, you might be talking about something like $20,000. Okay. So it turns out that in the case of an electric car, once the nominal capacity of the battery reaches something like 80% of its original capacity, then it is no longer suitable to be used in the car. Okay, because you are just carrying too much dead weight, right? So the charge capacity is not optimal anymore, right? So you should change your battery and have a new one. So the first question is that, once that happens, we have lots of electric cars now in the US, a lot of them in Germany. So, in a couple of years, we will see a lot of these batteries that need to be replaced. So what do you do with so many batteries, right? So either you could recycle them, like, scrap them and use the materials and build new batteries. This is going to be expensive. Also, it has a big environmental impact. Or we could actually reuse those batteries and use them for stationary storage. This is a second life usage. That could be another possibility. This way you prevent the recycling so quickly. Or we could actually also build better kinds of batteries. Okay, and I'm going to briefly give you some ideas and what kind of problems exist there. So in an electric car, you have a battery pack. So that battery pack is not just one giant battery, but it is made up of many smaller batteries. And these batteries, many of these batteries are connected in series. So depending on what kind of voltage you need, you connect them in series. And depending on what kind of current you need, you connect many of these chains in parallel. Okay, so your big battery pack is made up of a large number of series and parallelly connected batteries. Now, ideally, all of these batteries are identical, but in reality, they are not. There is a lot of manufacturing variability. in the pack, depending on where the battery particular cell is located. Its temperature profile is very different. So these batteries are going to age in a very different, in a very different way. And there is something called a battery management system that continuously monitors each of these batteries, monitors their, aging, charging, discharging profiles, their temperatures. And this is what is called a battery management system. Okay. And currently what happens is that for every battery pack, there is a tailor made for that pack or that specification, there is a battery management system. And instead of having this, so therefore, for either you could have what is called a centralized battery management system, which is monitoring all the cells, or most normally you are going to have a slightly distributed battery management system where a large number of cells are being monitored by one BMS. But however, what is happening is for every battery pack, there is a custom designed battery management system. So for your laptop, there is a different battery management system. For your electric bike, there is a different system. For a car, there is a different system. For a truck, there is a different system. So as a result, you are, and the battery management system is also relatively expensive. It sort of contributes to a large cost of the total battery system. So the first thing that we try to do is that, why not design a battery management rather than having a separate battery management system? Why not integrate the battery management system in the cell itself, right? So the main idea is that you make the cell more smart, right? So you can add a small microcontroller, some memory. So each cell then monitors itself and records its status in the cell itself. And now the first advantage you are going to get is the battery is going to become modular, right? So now you don't have to design a battery management system for the bike battery and a car battery and a truck battery, but you just put together these intelligent cells and they should be able to, just using software and algorithms, they should be able to reconfigure and develop like a distributed battery management system on their own, right? And this is going to reduce costs, but this is also going to do lots of other things. And the first thing it can do is it can, so when your electric car battery ages, you can take out this battery and now each cell has information on what has happened, right? How many times it was charged, how many times it was discharged, how long did it take to charge and discharge. It knows about its age, it knows everything about its temperature. So you could figure out, okay, among this, 700 cells that are there in the pack, these 10 do not look very good, right? The remaining 690 are probably still perfectly fine. And if you have the proper electrical architecture, you could actually just bypass those 10 and still keep on using that battery, and it is probably going to last you for another couple of years. So there is a huge amount of advantage of making these individual cells a lot more intelligent. The other interesting thing that happens is that because each cell turns out to be very different, although when you start, you have the same amount of charge in every cell, when you start discharging the battery, each cell is going to discharge at a very different level, right? So what might happen is there is a lot of charge left in one cell. There is a lot of charge left in all the cells, but just one cell kind of goes down to a very small level. Now, if you keep on discharging the battery, then you are going to damage this cell and you are going to damage the entire pack. Similarly, when you are charging, maybe one cell reached a high level, but many of the others are at a lower level and you cannot charge this anymore. Now, in order to prevent that, so because of the things that I already mentioned, and this is what is happening, and because of this, the kind of things you'd like to do is you'd like to do what is called a cell balancing, right? Which means that either you could do what is called a passive balancing, which means you burn out the excess energy to bring everything to the same level. This, of course, is very wasteful, and also it generates a lot of temperature, which is bad for the battery pack. Or you do what is called an active balancing, which means that you are going to transfer some charge from one cell to the other, right? And this is what is going to happen. You transfer charge from one cell to this, or you transfer from this to this. And here there are lots of interesting, so currently there is a lot of work that is being done, and there are different problems that exist. So first of all, what is the electrical architecture using which you can do this balancing, right? You cannot just directly transfer charge from one cell to the other. There is a lot of power electronics that goes behind this. So you will have to do something like you have a capacitor. You first have to charge the capacitor, and from the capacitor or an inductor, you transfer the charge into the other cell. Now you could do something like either you transfer some charge from this cell to a far away cell. Now, if you do that, the longer the distance, the more is the energy loss. You can decide on at what current you are going to do the transfer, right? And if you use a very large current, the transfer is going to be fast, but again, it is going to lose a lot of energy and the temperature is also going to rise, okay? So the kind of parameters that are important here is you'd like to bring all the charges to the same level, but you'd like to do that as fast as possible. So you'd like to minimize the balancing time, and you'd also like to minimize the total energy loss. So therefore, you have all these strategies like, you do a neighbor to neighbor transfer, and then from there, or you do a far transfer. There could be issues like if there is a transfer between this B1 and B3, then at the same time, you cannot do a concurrent transfer from B2 to B4 because that path isn't available anymore, right? So then depending on the architecture, there will be lots of different constraints, and you have to figure out what is the right kind of balancing you'd like to do. And there are also other things I don't want to go into, but things like if you do too much of balancing, you are doing a lot of writes and reading and writing of the cells, then you are also doing aging because of that, right? So how do you also minimize that balancing induced aging and the usability of the battery? So as I said, there are lots of problems in distributed algorithms here. There are problems related to electronics or power electronics that are there. There are problems related to control that are there. We have actually built a prototype. So these are the individual cells, and this is the electronics that is going to make it smart. So in this prototype, that electronics is sitting outside, but the future is that this electronics is going to get integrated into this. And then we also have a software using which we can monitor which cell has how much charge, and then you can see, try out different algorithms on charge transfer algorithms on this prototype and see how much time does it take, how much energy is being lost. And there is a small video that shows this. So this is the board where you have, and this is our software, and you can change different parameters in terms of how the transfer is going to be done. And then you can see what kind of transfer is happening. So you also have a model of this, and you can see what kind of charge transfer is happening. And each of these cells also have a small display that is going to show what is its charge level and in which direction the charge transfer is happening with those. So these are the displays, and you can see that there is current coming in here, or it's going in the other direction. Right, and but this is just a start, and there is a big need for this in the industry. There are lots of different problems, as I said, both in the domain of electronics, but also in the domain of distributed algorithms, formal verification, modeling, control, etc. So with that, I know I couldn't limit to the 45 minutes that Mike gave me, but that's all that I had. Thank you very much.
Any question?
Yeah, yes.
So this is kind of an overarching question across all of our domains, but for each of these cases, you have some balance between how much you are doing in order to optimize the system and how that affects the system itself. Like in the case of the battery, if you put the systems on it, all 444 18650 cells in a Tesla, that's quite a bit of electronics that adds to the weight of the car. And similarly with the Android system, if you're running an optimizer on the CPU that it's optimizing for, wouldn't that also affect how much CPU it's using? How do you balance the complexity of these systems with how much they save?
Yeah, I think that's a very pertinent question. So let me try to answer the first one about adding the additional electronics. So the weight of the battery is actually a lot, right? So the battery weighs a lot more than, each cell is going to weigh more than a very small, simple microcontroller. There is already a battery management system that is there in the system, right? So you cannot not have any electronics. So the electronics is already there. As I said, the current architecture is that there is a centralized battery management system that is monitoring everything. So there has to be wiring between this centralized management system and all the cells. Or there is some sort of a hierarchical management. There are multiple battery managers, then there is a centralized. So there is already electronics, there is already wiring, but the system is not modular. Whereas what we are saying is that rather than having one big piece of electronics, can we break it up into smaller electronic components and integrate them into the cell? So it is not clear, we haven't quite done that level of calculation because we only have very rough prototype systems. So it is not clear whether by doing what we are proposing, we are going to increase the volume of electronics. It could very well be that we would actually reduce the volume of electronics. But then there will be more complexity added in terms of algorithms and software, right? Because having a centralized algorithm is always going to be much easier, whereas now we are talking about a distributed algorithm. So we might even have to give up on some efficiency, but there are lots of benefits in terms of, as I said, modularity. Right now, you could now put together different battery packs and it would now work much better. So yes, and also there are lots of other advantages, as I said, right? If you are doing a second life usage of the battery, or if you are recycling, then if each individual cell can store its history, then it's much easier to read that out and then decide, which cells you are going to use, or maybe, reconfigure the battery pack so that the very old cells are not used, and you have a slightly smaller capacity battery pack that you can use in a different way. There are also many interesting problems out there I didn't have a chance to talk about. So I think there is a huge potential out there on battery insurance. So we have spent some time looking at the insurance or the conditions, guarantee conditions that Tesla gives on their batteries. Now, as I said, right, there is a lot of manufacturing variability that is there. How your battery is going to age will depend a lot on how you drive the car. It depends on where your car is parked. Do you park it inside or outside? Are you parking in Saudi Arabia or are you parking in north of Sweden? And therefore, as a result, what kind of temperature it is getting exposed to. So it doesn't, so depending on the usage, your battery might last for 3 years or 5 years or 10 years or 15 years. But however, you buy the car, you do not know this, you use it, and then there will be some users whose battery is going to get replaced in 3 years, and they will have to probably shell out this $20,000. It's not clear whether it is because how they use the battery or whether because there was some manufacturing thing. So there is a big case of having some sort of an insurance, right? That you buy your Tesla, and if the battery doesn't last for 2 years, then they are going to, the insurance company is going to pay for it. Now the question is, in that case, how do you determine the premium? And there, I think there is a lot of potential in terms of measuring how the battery was used. How did you accelerate? How did you decelerate? How, where did you keep your car? If those things can be measured, so it could be something like, the first year is a standard premium for everyone. 1 year later, you take the car to your workshop, and they can read it out from this kind of, if you have the kind of cells we're talking about, they can very easily read out what the battery suffered, how the battery suffered in your hand. And then they can decide, what kind of premium you have to pay for them. So I think a lot of these possibilities are going to open up with this more intelligent battery cells. So I would not worry so much about the weight of the electronics. For the other things, in terms of how much additional computation we are adding for power management, I think currently most of the things we are doing are relatively simple. The kind of predictors we are using are relatively simple. If you use more complex machine learning techniques, you are absolutely right. Here we have to be careful about what we use, such that the prediction technique itself does not add too much work.
Any more question? Yeah.
Yes.
So I have a question, I suppose, is, let's say I have some software and I want to design some intelligent power management system for it. Can I think of it adversarially and try to be like, okay, by just looking at how much power is consumed, can I try to infer some sensitive information about what the proprietary software is doing? Or try to find out some information?
Yeah, I mean, there is a lot of work out there exactly on that, right? That getting some sort of side channel information. If you can, measure the temperatures the processor is experiencing, or if you can measure some leakage current, from that you can infer what is running. So yeah, this is what you are saying is a valid issue, but people have been looking into this for a long time.
Any more question? Okay, let's thank Samarjit again. Thank you. And it's gonna stay here standing for another 15 minutes.
Okay.